All right, guys, some tips for taking your tests. First of all, make sure you don't leave anything blank. On the free responses, hopefully there won't be any, few if any, questions you don't know how to do. But if there happens to be one you don't know how to do part of, make sure that you at least write down the formula that you know you need to use, solve it for the variable that they ask you to solve for, and insert as many of the numbers into the formula as you can. A lot of times you'll get a point just for writing down the formula. Sometimes they're requiring you to actually make an effort to solve it. So make sure, insert numbers into the formula. One of the most important things for you to do to succeed on the multiple choice part of this test, memorize the formulas. Look at that formula sheet I gave you, and make sure you know those formulas. A lot of them you'll know already, but take the time to study them. And then the other thing, make sure you use that review book. Study, in particular, optics and magnetism. Other than the time you spend in study sessions here, spend a lot of your time at home looking at those two topics. All right, we're going to work a few problems. First one, a block of mass M is resting on a horizontal table of negligible friction. The string is tied to the block, passed over a pulley, and another block of mass 5M is hung on the other end of the string. Find the acceleration. So we've done problems like this probably 100 times. This one doesn't have many numbers in it, which is the way the multiple choice section seems to be going. So we have a mass up here on the table of 1M. And it's pulley and string. And hanging on the edge of the table is a bigger mass of 5M. And we're supposed to find the acceleration of the system. All right, there's no friction between the table and the box on top. So the thing that's causing these boxes to move is the weight of that box right here. So the weight of this 5M box, that's the net force. So our net force is going to equal the weight of that box, which is 5M times G. And that net force is acting on the whole mass. The whole mass of the system is 6 kilograms. Or not 6 kilograms, 5M here, 1M here. Which means our acceleration is going to be net force, which is 5mg, divided by mass, system mass, which is 6. That's as far as we can go with the acceleration. A equals 5mg over 6. All right. The next part says draw a free body diagram for each block. So let's start with the one sitting on the table. One sitting on the table, we've got the weight acting down. You guys who are in here, what's acting up? Normal force, equal, opposite. Those two cancel out. And then we've got acting this way, what force? The tension in the rope. That's it. For the one hanging from the table, the 5M mass, we have weight acting down, and we have what acting up? Tension. Which one's bigger? The weight, because there's a net force, right? So this is weight, and this is tension. We don't really have any forces acting side by side, so those are our free body diagrams. Last question is find the tension. And we can do that in two ways. The easiest way is to think about it in terms of this. Because what we have acting down, we have a weight on that box of 5mg acting down. We know the tension is acting up. The difference in those two things has to be what? A net force. So we could write an equation. Net force is equal to weight, which we know is bigger because it's falling, minus tension. Which means tension is going to be equal to weight minus that net. We know the weight. The weight is 5mg. We also know the net force. Now it's just the net force acting on that block here that matters, all right? On that block, on this block, the block hanging from the table, what's the net force acting on that block going to be? The one hanging from the table. It's going to be 5 mg, the mass, times what? F equals ma. So it's going to be 5 mg, or 5 m rather, right? 5 m's the mass, times the acceleration, which is 5 mg over 6. So our net force on that block is going to be 25 mg over 6, which means that our tension is going to be 5 mg, the weight, minus 25 mg over 6. Does that make sense? Let's try a completely different kind of problem here. This time a boy climbs up on the roof of a house and he drops a ball. It's 7.5 meters to the ground. How fast will it be traveling when it hits the ground? There's 2 ways you could work this. The way that might come to mind first is what for you guys? Yeah, use the kinematic equations, all right? That might come to mind. But I think the way that they want you to work this one, you could get a kinematic equation problem, no problem, make it work. But this, if you look at the rest of these problems, they're about energy. So when you're up on top of the house, what kind of energy do you have? Potential. And by the time you hit the ground, what do you got? Kinetic. So they're wanting you to set those 2 equal. But the potential energy at the top of the house is by the time it hits the ground, it's all kinetic. What's the equation for potential energy? mgh. We're going to set that equal to 1/2 mv squared. The masses cancel, so we end up with gh equals 1/2 v squared. We're trying to find a v, so let's multiply both sides by 2. So 2gh equals v squared. V equals the square root of 2gh. So if we put some numbers into that equation, v is going to equal 2 times 9.8 times 7.5. And we're going to take the square root of that. And when we do, 2 times 9.8 times 7.5, square root both sides, or square root, yeah, both sides, 12.1 is what we get. And remember that velocity is a vector, so we need to say down, or put a negative, or put an arrow. All right, with the help of a friend, the boy measures the height to which the ball returns and finds it to be 5.2 meters. So it hits the ground and it bounces back up 5.2 meters, not 7.5 meters. How fast was the ball moving when it left the ground? So when it left the ground, what did you have? You had kinetic. And as you move up, you're getting more and more potential, right? So this is where you're going to say kinetic energy to begin with equals potential energy to end with. Or you could use what? Kinematic equation. Either way works. I'm going to do it this way though, since all the problems are energy. So again, I'm going to say 1/2 mv squared equals mgh. And we're going to end up solving the same equation, right? V equals square root of 2gh when we solve it out. So V is going to equal the square root of 2 times g, 9.8, times h. This time h is 5.2. And we end up with 10.1. So the ball, when it hit the ground, was going 12.1 meters per second. What happened when it hit the ground? As it was hitting the ground, what happened to the ball? Compressed. And it popped back off the ground going slower than when it hit. So some of the energy got what? It got lost. And we might as well go ahead and answer this question. Where does that energy go? Sound or, which would be heat, right? Sound or heat? Let's go ahead and answer the middle question there. How much mechanical energy was lost? Mechanical is just potential and kinetic put together, right? So it'd probably be easier if we just calculated, we could calculate the kinetic here and the kinetic here and the kinetic here and just subtract them. But it might be easier just to calculate the potential here and the potential here. So let's calculate the potential energy at 7.5 meters. We'll just do MGH. So at 7.5 meters, we're going to take 0.40 times 9.8 times 7.5. And we get 29.4. Now that's at 7.5 meters. At 5.2 meters, M, 0.4 times 9.8 times 5.2. So there we got 20.4. So somewhere in the meantime, we lost what? We lost 9 joules of energy. And that's our answer for the middle question. You guys good with that? All right. Torque problem. So we got a seesaw. I have a 20 kilogram board set with its center on a support. So that's like the fulcrum of the seesaw. On one side, we put a kid of mass 30 kilograms, 2.5 meters from the support. I'm going to draw this a little bit lower. So let's say this is the 30 kilogram kid, and the distance from the kid to the center is 2.5. All right, a second kid sits on the other side, 15 kilograms, and he's sitting at the same distance from the support. So he's also sitting 2.5 meters from the center. Right now, is the seesaw balanced? Definitely not. Because there's a net what over on the left side? Which leads to a net, what makes things spin? Torque. There's a net torque. We calculate torque by saying force times distance, F times R. So what we want to know is we've got a third kid, we're going to sit him on the seesaw, and we want to know where the third kid needs to sit to balance it out. For it to be balanced, torque over here has to equal to torque over here, correct? So we can calculate the torque on this side. Torque on this side is going to be not 30 kilograms, but we need force, right? So it's going to be 30 times what? 30 times 9.8 to get the force. It's 294 newtons times the distance from the center. We use a marker that will actually show it here. So 294, that's the force, times 2.5, distance from the center. We know the other kid's got to sit on the right side, right, to balance it out. So we're going to have over here 15 kilograms times 9.8. That gives us 147 newtons times 2.5, the distance, plus the weight of the 20 kilogram kid. So 20 times 9.8, you get 196 times some distance that we don't know. That's what we're trying to find. So if we solve this out, let's go 294 times 2.5. Let's subtract from that 147 times 2.5. And then let's divide that all by 196. And I'm ending up with a distance of 1.88 meters. I want to check my math there, though. I'm afraid I messed up on the calculator. So let's go 294 times 2.5 minus 147 times 2.5 divided by 196. And yeah, 1.88 is the distance. Make sense? Torque, for it not to spin, torque has to equal torque. Clockwise torque has to equal counterclockwise torque. All right, we just did one like that, so let's do this one. Here we have two capacitors. Two capacitors in parallel, and then that parallel unit is connected in series to two more capacitors. First of all, draw the circuit. So our circuit model looks something like this. Here's our battery. There's one capacitor. And there's another one. And those are hooked in parallel. And then they're hooked in series with two more. Something like that. So one of these is 1 microfarad. One of them is 2 microfarads. And then these other two are 4 and 6. Remember that the rules for capacitors are opposite of the rules for resistors. So if they're hooked in parallel, what do you do to find parallel resistance? Add them up. So the resistance of this whole parallel piece is just 2 plus 1, 3 microfarads. And just like we do in regular circuits with resistors, we're now going to think of that like what? The circled part. Yeah, we're going to think of it as one series capacitor, right? And when you're trying to find the series resistance, to find the series capacitance, right? To do that, we have to use the whole 1 over thing, the inverse thing. So we're going to say 1 over that parallel branch, 1 over 3, plus, just 3, plus the next one, 1 over 4, plus the next one, 1 over 6. We get a common denominator of 12. So this is going to be 4 over 12, plus 3 over 12, plus 2 over 12. Add those up, we get 9 over 12 equals 1 over our series capacitance, which means our series capacitance is 12 over 9, or 4 over 3. And that's microfarads. Does that work? All right, let's do maybe 2 more. This problem we've worked a few times, but we're going to look at it again. The circuit consists of a 100-volt battery hooked in series with a 20-ohm resistor and a 10 microfarad capacitor. For time equals 0, find the current and potential difference across the capacitor. So let's draw it out first. We've got a battery. Battery's 100 volts. It's hooked up with a resistor, which is 20 ohms, and a capacitor, which is 10 microfarads. First of all, we want to find the current and the potential difference across the capacitor. Here's the thing. When you first hook up a capacitor, when you first turn the circuit on, what's the capacitor act like? Piece of wire with how much resistance? 0. So this is like 0 resistance, which means the only resistance in this circuit is coming from where? 20 ohms. So if we want to find the current, we go I equals V over R. Ohm's law. We take 100 volts, our battery voltage, divided by our circuit resistance, which is 20, and we end up with 5 amps. So that's the current. Since the resistance of this thing is 0, what's the voltage across it right now? Nope. None. So the answer to part 1 here is we got 5 amps of current, and the potential difference, the voltage, across the capacitor is 0. Which means what's the voltage drop across the resistor to begin with? If there's 0 voltage drop here, how much voltage drop has to be here? All of it, right? So 100. But as time goes by, which is part B is about, what starts building up on these two plates? Charges. And those charges start doing what to the other charges trying to get on them? Repelling, resisting them. So eventually, what happens to the resistance of that capacitor? It approaches infinity. And when that happens, what happens to the current? There's no current. If there's no current, what's the voltage drop across that resistor? 0. All the voltage is across the capacitor at that point. So the answer on the second part, or part of the second part, the potential difference across the capacitor after some time is taking place is 100 volts. So that's our delta V across the capacitor. The second part wants to know the total charge stored on the capacitor. What's the definition of capacitance? C equals Q over V, right? Wait a minute, did I do that right? Is that right? So here's the thing, we're trying to find Q. So we're going to rearrange that, and we're going to say Q equals C times V. We know the voltage is 100. C is the capacitance. The capacitance is 10 microfarads. So that's 10 times 10 to the what? Negative 6, right? Farads. So if we multiply 100 times 10 times 10 to the negative 6, we get what? It's just going to make that power go up 2, right? So it'll be 10 times 10 to the minus 4. So the answer to the second part of this question is Q equals 10 times 10 to the minus 4 coulombs. And in the last part, find the potential energy stored. This is where you got to kind of know an equation, and this is one of the ones on your formula sheet that I asked you to memorize. It's the energy stored on a capacitor. What's the symbol for potential energy? Nope. U. U equals 1/2 CV squared is the equation you need to know here. Where we take the capacitance, which is 10 microfarads, which we're going to write as 10, try that again, 10 times 10 to the minus 6 times 1/2 times not the velocity, what's the here? The voltage squared, so 100 volts squared. Multiply this out, so let's go 100 squared times 10 times 10 to the minus 6 divided by 2. And we end up with not a whole lot of energy stored here. We end up with U equals 0.05. And if we use all the right units, if we use coulombs and farads and volts, we should get what energy units? Joules. All right. How's that working? All right, I'm going to save these for tomorrow, so I think that's where we're going to stop.